I want to thank for this opportunity to talk about a subject that also is not my main focus in research, is very close to my heart. And if this is about my original work on the generalized spectral kurtosis estimator. So what I'm going to present you today is a tale about a well-known radio data analysis challenge. And here is trying to picture myself in December 6, 2006, when we got one of the first test data from the prototype of what is now the Owens Valley solar array. And this data happened to be taken during the largest ever recorded solar radio burst in history. And during this event that happened on December 6, 2006, it's a chunk of data. Time is going in this direction, frequency in this direction. It's around 2 gigahertz. And you see a lot of features in this spectrum. And the problem when we first saw this data were to ask ourselves, what can we do with this data? How we can understand what is actually real solar data and what is called radio frequency interference. And this is a well-known data challenge, but what I'm going to show today is about a solution that is not so well known so far. And this is a method that implies statistical discrimination of radio signals. And if you apply the right statistic, I will demonstrate you that you can separate the astrophysical signal from radio frequency interference, even if they may feature the same frequency or time variations, so you see that would be very easy to confuse one with the other, especially if you want to do it in real time. Of course, a trained eye can tell you, okay, this looks like real data if you know what to expect, and this looks like radio frequency interference. But in terms of real-time operation of an instrument, you'd like to know to have an algorithm that is doing this for you. And to do that, I will just start with FFT spectrometer design 101 lecture. So the idea is that when you take a fast Fourier transform to build a radio spectrum, this is what you are dealing with. You have your signal here, but you have a lot of noise. And this is well known because if you take a time series that has a Gaussian distribution and you do a Fourier transform of it, you get an exponential distribution which has a variance that is as large as its mean. So that means that your real signal may be buried in 100% noise. So what you do in a classical design after the filter bank, actually you do an accumulation of your spectrum. So you accumulate the raw spectra, and you get an accumulated spectrum, an average spectrum if you want, or this sum, which we'll call it S1. And when you do that, you see some spectral features in your here that are easy to distinguish against the noise level. But when you do that, and this is what all classical instruments do, you lose something. You lose some important statistical information about the signal. And that's why what we proposed at that time was to actually accumulate not only the power, but also the square of the power. So, and this might be like a trivial operation. You double the data, what do you gain? You get two spectra that look alike. But here comes the magic of statistics. You just build the spectral kurtosis estimator, which is just a combination of these two sums. Actually, if the S2 divided by S1 squared, and you get something that is flat everywhere, except for some feature in your spectrum. And you see already a difference. You see this peak here, which is very clear seen in power, is absent in spectral kurtosis. And this one has like a spectral kurtosis that is below unity. And what is nice about this statistical estimator, that when you have a Gaussian time domain signal, it has an unbiased unity expectation. And you also can define its variance, and you can deal automatically with such signal and actually distinguish one type of signal from the other. So, excuse me? M is the number of spectrum that you add, yes? So, and of course, statistics depends on how long you accumulate. And in solar radio physics, you don't need to accumulate so many. I know that if you go to radio astronomy, like you look for deep space signal, you may want to accumulate for a long time to get your useful astrophysical signal out of noise. But it's the same operation. You add it, but when you add your spectra, you lose that statistical information. And what I want to show you is what we can do. So you can have the power, and you have the SK flags that tell you that is something different for this spectral peak compared with from the red to, compared with the green one. And the difference is in statistics. It's just because, in fact, one of the peak, the green one, obeys an exponential distribution, which is basically a chi-square distribution, a central chi-square distribution, while the other one, which is nothing else than man-made signal, usually obeys different distribution. And in the case of, for example, a sine wave or so, it can be demonstrated that this distribution is actually a non-central chi-square distribution. So this is the only difference. When you look at the one spectrum, they may not look very much different, except for some details. But when you try to accumulate, again, they might look similar. You have spectral peaks. This is the distribution when you add 100 spectra. And this is the expression of this distribution. But when you compute spectral kurtosis, something you can see, if you have a Gaussian signal, spectral kurtosis is 1, unbiased, plus minus a variance that depends only on the number of accumulations. While if you look at the spectral kurtosis expectation for this time of signal, the RFI, you get 1 and some complicated relationship in which you have the number of accumulation, but you have also the signal to noise ratio of your RFI. And this is just the first term expansion of this uncertainty. So this is actually the XK, and this is the variance of this estimator in this particular case. And this depends on the number of accumulation. When you accumulate, you get different values. But what is important, no matter how long you accumulate a Gaussian signal, you still get 1. And when you accumulate an RFI, it gets to some asymptotical value, which is less than 1. And at some point, after a certain number of accumulation, you can clearly distinguish one from the other. If you don't accumulate enough, they can still overlap statistically. But what we are looking for is this optimal range in which we can unambiguously discriminate them. So, of course, this is a natural signal. This is radio frequency interference. And this is the expression of unbiased estimator, which actually is the unbiased estimator of the variability of an exponentially distributed random variable. And basically, it's expectation of variance over squared mean, which you expect. This looks very simple, but in fact, it's a non-trivial mathematical operation. Excuse me a little. Which requires a lot of work. And actually, I did study this distribution for 15 years now, and I published more than 10 papers on spectral kurtosis theory and its application. And there are different aspects that may be interested from different science applications. So it's not like repeating the same thing, but different aspects of this. So you are welcome to scan this. This is my personal library. You can download them all and see if there is one that you think would fit your type of data. Because I will show you that it can be applied, this formula not only to radio data, but also to any time series and any time series of random variables. So, and to do that, actually in 2010, we published a paper in Monthly Notices that is called the Generalized Spectral Kurtosis Estimator, which tries to apply the same mathematical formalism not only to Gaussian distribution, but in general to any signal that obeys actually a gamma distribution characterized by a shape parameter d. So when you have an exponential distribution, d is 1. But you can have data that obeys a gamma distribution, and that d would be different than 1. And what was our main result reported in this paper is that actually you can compute the infinite series of this ratio, S2 over S1 squared, if you have a set of gamma distributed random variables. And if you know the full series of these moments, actually you can compute, you can define an estimator that has an expectation 1, and see we have the shape factor here, which is 1 if it's an exponential distribution, is something else if it's a different distribution. And most importantly, you can compute some threshold and the probability of false alarm for those thresholds, because you know now the statistical distribution of the estimator itself. So instead of doing some kind of empirical thresholding, you can apply the analytically defined threshold. And here is actually the distribution of the spectral kurtosis estimator. And you see that distribution depends on the number of accumulation. And depending on your application, you can say, okay, I can accumulate 1,000 of spectra, and my distribution becomes very much like close to a Gaussian, but it's not really that. Actually, you can look that it has a non-zero skewness, no matter like how long you integrate. But especially when you don't have enough data and you want to add only, let's say, 30 spectra, in this case 32, you see that the distribution is not symmetrical, and actually the detection limits for a given probability of false alarm are not symmetrical. So you have to know where to clip your data, not to throw away more than you want, and to see that you have some statistical results. So the code to compute these thresholds is on my GitHub webpage. And I want you to show some cases of well suited for SK analysis. For example, if you have raw power estimate based on time domain serial signals, then those samples will obey a gamma distribution of shape factor 0.5, which is a chi-scale distribution. We already discussed about the exponential distribution when you have a shape factor equals 1, or very interesting, you can actually do the same trick with already accumulated data. So when you accumulate exponential variable from an exponential distribution, their sum actually obeys a gamma distribution of shape factor n times d. So in this case, would be n for n distribution. And you can apply the same formalism, and you can do a discrimination of that. I will show you an example. So also, you can do this mathematical exercise with power estimate based on quantized time domain signals. And this is when you have an instrument that, in fact, doesn't have enough. You have like 2-bit resolution, 3-bit resolution. In that case, your spectra do not obey an exponential distribution, but they may obey something that resembles a gamma distribution of some shape factor that you can determine. And this is not the whole story. There is also a very interesting aspect of transient signal, of the one that I showed you. In fact, when you integrate, you may have a transient signal that happens during your integration time. And once you integrate, is there. But is something wrong? Okay, so your signal is there, and it has what we call a duty cycle. How long is stays your signal in your integration? And depending on the duty cycle, actually spectral kurtosis may have different values. For example, here I have a duty cycle that goes from 0 to 100, and you see that in the case of a Gaussian signal, and you may have spectral kurtosis that is not 1, just because it varies, it's not steady state. But it's important to see that you know what would be the shape of that. And you can compare with the expected spectral kurtosis for a non-Gaussian signal. They may look similar, the green and red curve, but there is a very important difference. And the difference is here. When you integrate a Gaussian signal, your spectral kurtosis goes above 1, can go down to 1, but never below 1, except for statistical fluctuation, but you know what they are. While the radio frequency interference or some other signal, they may go below 1. And this is a region in which you can clearly distinguish between them. Even if you have a flag, but you have to make sure that your flag tells you what. So the idea is you can do integration over various lengths, and you look at the distribution of spectral kurtosis. You have an adaptive search, and it's very easy to do that because, in fact, when you have sums S1 over a given length, you can add S1 with S1, S2 with S2, and you can have double, triple your M with the same data. You don't have to take other data, but you can algorithmically, in real time, do this kind of adaptive search to characterize your signals. So this is another monthly notices paper in which I discussed the spectral kurtosis of transient signals, and this is the expectation for Gaussian. This is for non-Gaussian, and these are the variances of these two estimators. And I think this is very important. Again, everything in terms of signal-to-noise ratio and the integration length. And now I want to show you actually the first prototype of an instrument that is doing real-time detection of radio frequency interference. And what you will see here, you will see a spectrum. You will see interference, continuous interference here. And you will see some interference that happens when we start talking on a cell phone. And here you will see a dynamic spectrum, and here the flags that the spectral kurtosis will produce. And you see these continuous RFI, they have less than 1 spectral kurtosis. They are continuously flagged here, here, and here. And now we start talking at a phone, and you see these transients. But the algorithm actually flags each transient over a 20 millisecond integration time. What is important, you flag a 20 millisecond time bin, but next time bin, the signal might not be there because you have some intermittent interference. And this allows you to look through interference. So without, you don't lose the, what you would do if you flag based on power, you can wipe up your entire spectrum like here. But actually in this region, even if you have intermittent interference, you can pick up those time frequency bins which are clean, and you can look at your data. And based on this,
can I ask a quick question?
Yes.
So the focus on real time is because you wouldn't want to do it as a post-processing step because you just have to store too much data, or wait, I'm not sure that I totally, I'm not very familiar with.
Okay, let me tell you what is, of course, when we started this instrument, because I'm going to talk of an instrument, and the way you do this spectra, you do a very fine frequency structure, and some of the channel may be affected by RFI. So if you are able to flag them in real time, you can get them out of your data, and you can integrate over the science band, and you keep in that science band only the signal that is not affected by interference. And because you cannot afford to keep all the data. So for this reason, you want to do it in real time. But if you want to do data analysis or something, for example, you have now telescope that actually log the raw voltages. Yes, in that case, you can do whatever you want, but you still do an analysis of your signal. So this is the importance of real time. And real time means, I will show you immediately, because this is an instrument that at NJIT, we have been working for the last 15 years, actually. I told you that in 2006, that one was a prototype. But now we have an array of 13 antennas that produce every second an image of the sun at several hundreds of frequencies, if you want, and in 1 to 18 gigahertz range. So basically, with this frequency, we can infer a lot of properties of the solar corona and so on. So we can do what is called magnetography, because you know that electrons gyrate in magnetic field. So basically, if you look at the gyrosynchrotron emission mechanism, it's depending on many factors, but the most important on magnetic field. So actually, we are able for the first time to measure the magnetic field and its time evolution in solar corona. This was a paper in Science that was published last year. So it was a breakthrough result. Now, I don't want to get in detail, but I want to tell you that, yes, it's what we have. We have these antennas. We have basically a correlator that accepts 16 inputs, but we have only 13 antennas at this point, and one big antenna that is used only for calibration, because you cannot, it has a helium-cooled receiver, and you don't look at the sun, you look at the calibrator, and you calibrate your antenna in order to make images. Now, what is different about the correlator at EOSA is that actually, instead of being a classical one that it gives you cross-correlation visibilities and also autocorrelation product, also it produces not only the integrated power, but integrated squared power. And we log that one, and we can do this kind of analysis. And when we look at our data, we can throw away those frequency time beams that are affected by RFI. So this is an instrument that I'm very proud of because I've been working on it, and it actually, it does apply this method just to demonstrate the community that it's a useful thing to have. And this is an example of EOSA spectrum which you see, this is the shape, this is observation of the sun. Actually, this is a band affected by RFI. See, you have an arbitrary spectral shape. This is a sum S1, this is S2, and this is spectral kurtosis, which you see, no matter what feature you have in your spectrum, is flat one, except for your interference. And you can estimate what is the degree of contamination in your data. Yes, and you can flag those data and clean your spectrum. And what I told you already is that some instruments may not have this feature, like at the level of the FPGA correlator. You already get integrated data. Once it's integrated, you cannot do anything with it. But our work on the generalized spectral kurtosis estimator demonstrated that it can do the same thing with already integrated data, which follows a gamma distribution, not an exponential distribution. You sum the sums, you square the sum, you sum them again, and you get a generalized spectral kurtosis estimator. 5 minutes?
No, there's a question.
Okay. Yes.
Okay, just one question in chat quickly. Greg Helberg asks, is the performance of the spectral kurtosis dependent on the number of integration n? E.g., what happens when the distribution of unaffected data changes during the integration time due to day-night cycles or calibration errors?
Okay, so it's a very good question from my friend Greg Helberg, yeah, with whom we work many applications of spectral kurtosis, and we are still trying to address different aspects. Yes, the performance, actually, what the number of integration affect the variance of your estimator. Yes, but the performance is not that. It's not affecting. Why? Because if you know to compute the theoretical threshold, actually you have exact the probability of false alarm that you want. So, for example, if you need the standard 0.14% probability of false alarm, you can compute the threshold for your data, for the integration number that you have. If it's too small, they will be large, but still everything that goes above has that probability of false alarm. So it's the same performance in terms of course, there might be cases in which you prefer to have longer integration, but I'm saying that some other issue may occur, but this dependence on n, I would say no. But it may depend on signal to noise ratio, as I showed, because also if you have large threshold, your signal may be within the threshold, the one that you want to excite, so it might not work. But I want to show you here an example of raw spectra, and this is the one taken during a solar flare. And this is very important because you have a solar flare and you have something that you want to look at. You don't want to wipe, and your spectrum is not flat. You see evolution of your spectrum in time, yes? And this is a solar flare. These are low frequency, high frequency, but you have also interference. You see, here is the background subtracted spectrum. This is the raw spectrum. But when you look with raw spectrum, you can compute the spectral kurtosis, and these are the RFI flags. And you apply to your data, and what you wipe up from your spectrum is only those time frequency beams that are affected by RFI. And you see that you do not affect most of the astrophysical signal. And this way you obtain a clean spectrum. So we do images at each frequency time beam. We are not going to do an image in a beam that is affected by RFI. So but we have plenty of time frequency beams from which we can produce meaningful images. Okay. So that means that we can look at the spectral kurtosis as a powerful signal classification tool. And I will show you another example with Owens Valley data, where you have a raw spectrum with a lot of interference. You see, you can see them by eye, yes? The problem is how do you see them algorithmically. When you integrate your spectrum in time, you get something like this, and you get these lines in your spectrum. But you see that in reality, there are many different types of interference. Some is continuous, some is like intermittent. And when you apply the spectral kurtosis, it selectively pick up those beams. Not all of them. You have still valuable data in between that you can use. So this is the beauty of when you do a clean spectrum, what you do. As I said, you integrate over the science band, you remove interference, and you get a clean spectrum. There might be channels that you cannot do more than that because all the frequency are affected. When you do integration on science band, you still get nothing, but not everywhere. Most of the spectrum is clean. And here you know that you have some problem, but even here you can see the data through interference. Now, but when I say that spectral kurtosis is a powerful signals classification tool, it's not only that. You can look at the data in a different way. You put on one axis all the powers in your data, and the other one all spectral kurtosis for those powers. And when you look at the distribution, you see a very interesting picture. You see color-coded, you can find this signal here. You can see this signal there. And you see the time evolution, because these are all the spectral kurtosis in time, it's not one integration. And you see that some of them go above unity, some of them go below unity. Most of the data stay within limits, yes? And each of these is a different type of signal. It might be interference, might be RFI, an RFI transient, but maybe a Gaussian transient itself, and if it is in some region. So you have to understand your data and apply the right statistics. But looking at this diagram, you can see a history of your data, see what kind of interference you have in your data, or what kind of signal, because might not be only interference. It could be physical signal that obeys some statistic that is shown in this diagram. And this is very simple. So you just do this modification in your data pipeline. Instead of you have the time domain signal, you do the FFT, you accumulate S1, but you also accumulate S2. Using S1 and S2, you compute Sk, and after that, you can characterize your signal having S1 and Sk, both things which are actually are the outputs of our instrument. Now, you can go even further than that. So you can apply it even, there is a variant of the spectral kurtosis estimator that actually works with the kurtosis in the time domain. And that in one of the paper is described this. The generalized spectral kurtosis estimator works with time domain data with no spectral, like no FFT. You can just look at the time series of your data and you can build a so-called spectral kurtosis estimator, but just because it's the formal, a generalized spectral kurtosis estimator. There is no because the entire spectrum is in one band, so you don't have that frequency resolution. But what you see, you can see some transients in your data. Or you can look in the spectral domain, you can have very massive spectra, but again, this estimator will not, most of the cases, should not, if you do it right, would not wipe up your valuable data, but will detect what is not what you would expect in your data. You can do the same trick with images, series of images, and you can build a similar estimator, use the same mathematical formula. The only thing is you have to have a data that somehow is related to the gamma distributions. If you have a certain, you can approximate the distribution of your data. And maybe your data is not gamma distributed, but combination of the data, for the square of the data or the logarithm of the data, something. So you do a mathematical transformation to bring it as close as possible to a gamma distribution, and then you do this, apply this mathematical formalism, and you can build a so-called spectral kurtosis estimator and learn something from your signal. So you can even do a spectrum analyzer. You can listen to noises, and 10 minutes, thank you. I will try to. You can listen to, like, analyze medical signals. You can look at the, like, deep space signals, like FRBs or so, or even to ET signals. Because what is an ET signal is just radio frequency interference. So if they send a signal to us, it should have, if they want us to detect it, they may know the theory even. And they will send a signal that will be, if they want us to detect it, we should be able to detect it using this very simple mathematical approach. And I promise you to show you some real data. And here is a very simple exercise that I did with data from Park's breakthrough listen digital recording backend. And I thank you, my colleague Greg Helberg, because he provided me this data when he worked at that telescope in Australia. And actually, this is a dispersed FRB data. So you know how you do. You do your dispersion of the data, and you try to actually do the same operation, but instead of doing in time, you're doing across frequencies. So you compute the S1 across all frequency in your bandwidth, and you hope to see a signal like this. This is a real FRB burst. If you have interference, like here, when you integrate, you get something above the background, but it's everywhere. But sometimes if it's transient is not in this case, but if it would have been a transient RFI, you still see a peak and flat spectrum after that. The idea is, can we distinguish one from the other of doing this trick? So yeah, in fact, you can integrate across the band, and I did this simple operation, and you get the square power. And they look similar. And when you build spectral kurtosis, you see that for RFI and RFI case, spectral kurtosis, most of the values are above the threshold. And for this FRB signal, they are within the threshold. In fact, this is, I would say, an objective way to say, yes, this is what we expect from a natural pulse. We do not that obeys a Gaussian statistic. In fact, there was a paper about this particular FRB, because there was some kind of controversy. Somebody said that maybe this was some kind of interference, it's not a real FRB. And they tried to prove that it's a real FRB. But if they would have applied this method, they would have said immediately, yes, this is an FRB, because we do not expect FRB to look like RFI in terms of statistics. Okay, I try to finish. So another example from the breakthrough listen is another deep space radio signal captured by one of their instruments, in which actually here I didn't do any integration. What I did, I computed for this signal the power, dynamic spectrum, and the spectral kurtosis corresponding to that spectrum. But in this case, I had the luxury to have voltage data, so I can play with the M. If I integrated just M12 spectra, and I have a frequency resolution which is very high, 100,000 channels, and I have a frequency resolution 0.75 hertz and delta t between spectra 21. So the integration length is 21 seconds. And when you look at the spectral kurtosis, what you see is that you have everywhere within the limit, but you have some, and you have this clear data that is above the limit for what you see in the spectrum. So you ask yourself, what kind of signal is this? It's a drifting signal. Is this natural or artificial? Because both of them can have spectral kurtosis above unity. Remember from my previous plot. And you ask yourself, is this a natural or an artificial signal coming from deep space? And to solve this problem, you have to play with the integration time. And when you do find the right integration time, you end up with clear spectral kurtosis below unity.
Huh?
Question?
How much you know about that?
Sultan, can you mute yourself, please?
What? Okay, so you see that if you change the frequency resolution and the time resolution from 21 seconds to 5 seconds, you integrate for sure, but you reduce the number of frequency a lot. You can manipulate your data. You still get the same picture, but spectral kurtosis is not that it's below 1. So then you say, oh, what is this? For sure, you say it's not a Gaussian distributed signal. So should be a deep space technosignature. And I would have been happy to tell you now that we discovered an ET signal, but in fact, it's a Voyager 1 beacon signal that was captured by. But what is Voyager 1? It's a deep space technosignature signal because it comes out from our solar system, and we capture it, and we see that spectral kurtosis can tell us that this is, of course, if we don't know about it, but this was on purpose. This data was taken, but not to apply spectral kurtosis for others. So I did. I had the courtesy of this group. I got this data, and I was able to prove that this should work. Now, I have 5 minutes. Okay, one, good. I want to get a little bit more. What if we, for example, we have already integrated data, we have power and power square, but we cannot play with the trick that I said, like we don't have voltages data to play with. So then what you can do most is to continue integrate, like add S1 to S1, S2 to S2, and see how the power changes. So here is how the accumulation, when you increase the accumulation length, your signal power can increase. And let's suppose that in your time domain, you have a transient signal that lasts only from here to here, yes? And when you accumulate, you start to accumulate and you add to your background, you start adding your transient. And some point when you get to the other edge, you exit the transient and you start accumulating, continue accumulating, the power still go out, but you see, we have a pattern here when you cross the transient by doing this continuous integration. So that means that, in fact, doing that, you can have different duty cycles of your active signal for different accumulation lengths. And having that different duty cycle, you can compute spectral kurtosis for different lengths. And if this is a Gaussian transient, you expect to see this pattern going up, going down, and again up and down. This was in, but if it's an RFI transient, an artificial signal, again, it's going up, down, up, down. It might look the same pattern, but look at here. Is this region that is important? When your spectral kurtosis for a Gaussian transient cannot cross below unity, expect for some statistical fluctuation, while for the non-Gaussian signal, it will go below unity for a certain integration. And you do this with your data. So basically, you can have a pipeline that is doing this buffering of your data and on the fly can tell you, oh, I have something that is not Gaussian in my signal, yes? Or I can have a Gaussian transient. You can also detect it, and you can discriminate. So this is an example of such data. This is an FRB data, very bright pulse. And you see it in the spectrum. If you cross the spectrum at this frequency, you can see a clear peak and flat background. Now, what is important about data is when you compute spectral kurtosis for this data, you see nothing, except for RFI, which is here. You see, you have a bright pulse, you have no trace of an SK for FRB, so you have RFI. So you ask yourself, what is there? Why don't you have an SK there? Why is SK 1? It may be that it's Gaussian, but it's not the entire step, because if you go to the theory, you see that RFI, when it crosses from above 1 to below 1, it may be in a regime in which is still 1 and you don't detect it. So you are not 100% sure that this is Gaussian distributed signal. So you have to do more than that. And what I proposed in this paper was to actually do continuous accumulation of your signal, and you see the edge of FRB, and look at the pattern of your SK as your accumulation increases. And you see this pattern, and you ask yourself, is this one or this one? Again, is not the right one, because it's in this particular integration, you do not reach one or the other. But if you do the right accumulation and continue to this search, you get this pattern. And I would claim that actually if this pattern where you do not cross 1, you go up, down as you start increasing without getting below 1. And this is a clear signature of a Gaussian signal. So again, this FRB signal is Gaussian distributed. So in conclusion, I would say that due to its conception simplicity, Spectral Kurtosis Estimator is likely to become a standard tool that you use in this kind of analysis, but it can do more than discriminated RFI. It can do more, tell you more about your signal. So that's why you have this setup. It can be a hardware setup that is telling you what kind of signal you are dealing with. And I would say normally I would stop my talk here and say, okay, everything looks fine. But since we are here to discuss also some maybe intriguing aspects of it, I want to just finish this with an open question. I do not have an answer to it. I just came across it. And maybe somebody in this group might be interested and may try to do more. Because the question is, could a natural deep space signal obey RFI-like statistics? So there is any model that you can model a radio signal coming from a deep space object, which may show you something that is not Gaussian in their pattern. So it's not Gaussian. So, and you can do some kind, you can do modeling, you can do, maybe already you know the answer. I don't know it. What I know is that, again, it happened, I just came across this data, again, from the Breakthrough Listen team. It's a pulsar data. And you see here, you see RFI, clear, and you see your pulsar data. Of course, what you do next, you do spectral kurtosis if you have the tools to do that. And here is what I got. So RFI. Yes, but what is this? This is a region, so some portion of this pulsar data show clear less than 1 spectral kurtosis, which tells me, if I did the everything with no mistake whatever, I just say that I did a study, I applied the method, and it's just one case. So I cannot say that it always happens. But for this particular data segment, I come with this thing. So after all this dissertation about spectral kurtosis being above 1 if your signal is natural. Actually, I give you a counterexample, and now maybe a challenge. Can we, or can somebody model a natural signal that does not obey Gaussian statistic? And in this case, you should see the spectral kurtosis signature of it. Thank you very much for your attention.
Great, thank you so much. So if people in the room have questions, you can raise your hand and use your table mic. If people on Zoom have questions, please either raise your virtual hand and unmute or drop them in the chat. Yeah, Julianne.
Hi, this was really nifty. So I'm currently involved in an extremely large VLA project that involves tons of PhD level scientists staring and cleaning stuff by hand. I'm assuming we're stuck, you know, if this isn't happening at the accumulator level, there's nothing we can do post facto, or is there any lessons that have been learned from this that can be?
Okay. Yeah,
I mean, we spent the amount of person power going into eyeballing these things and identifying, flagging stuff by hand it's absurd. And
I know that actually that you need to do cleaning of the data, and especially in radio astronomy, that not in solar, it's very popular to do some kind of cleaning based on level of your power, and you see whatever is above certain value. It's an empirical method, yes. But
I wouldn't say it's popular as in people like it.
No, okay. I see many people. Okay, I don't know. It's not popular for me. I see that it's the way you do it, by so-called by hand and empirical approach. Yes, and I would say that yes, if you have the lecturers and instrumentals hours that was built to deal with this, it's one thing. But if you apply the generalized theory, you can do the same thing with your data. What is the cost of not having a dedicated hardware component that is doing that at highest time resolution level? Is that when you do that, you compute spectral kurtosis for a certain amount of time, while maybe your RFI is shorter than that. But you have to wipe up the entire segment, but not all. So you still can do this trick. So you can apply it.
So it still can work on accumulated. It's still useful for accumulated data. You can't recover quite as much information as you're able to if you're doing the time sequence.
If what I showed with the own valid data, this is experiment, what you do, you flag more data that would you do if you had that level of FPGA level, but it can be done.
That's awesome. Thank you.
We've got a Zoom question from Will.
Okay.
I'll echo Julianne. I think this is awesome. I am wondering, though, everything you have described uses power statistics.
Yep.
And I'm wondering if there's something equivalent or similar or useful in looking at phases. So something like the fourth moment of the phase minus twice the second moment. It's harder because phases are on a circle, so you'd have to use circular accumulants or something. But I wonder if that might prove fruitful, particularly for things like RFI, which are human or extraterrestrial made and would be phase coherent. Or, of course, as we were discussing in our nice conversation before your lunch, signals like LIGOs, which are also phase coherent because they're orbits.
Yes, it's a very good question. So I did not do myself this kind of work, but my answer is the theory of the Generalized Kurtosis Estimator is like this. If you have a set of random variables that you expect to obey a gamma distribution, you can directly apply this theory. So if you expect your phases to obey a gamma distribution, not a Gaussian one, a gamma distribution, because after transform, when you take your time domain data, you do a Fourier transform, you actually transform one distribution to another. You map it to another distribution. Now, if your data does not obey Gaussian gamma distribution, the trick that I would try is there is any mapping of your data that can take this distribution and get it through some mathematical operation in a gamma distribution. If you succeed to do that, you then can use that artificially constructed random variable and apply the statistic of spectral kurtosis and detect what. So, and if you are still here, I can show you some result with the gravitational data.
Oh yeah, that'd be fun offline. Okay, cool. Yeah, I'll think about that some more. There might be a way, like you say, to make some auxiliary random variable that lets you look at phases. Cool. Thank you.
Okay.
All right, it is about 4:30, so unless anybody has a last quick question.
I'm very curious about this. Oh, very nice talk, by the way. I'm very curious about the sources of RFI because I never think about this. But you showed, at one of your slides, you showed an example of a few different time-evolving spectra of different RFI classifications or something like that.
Yes.
Like one said zebra, something, burst. And
No, those there were real solar
those were
data.
real. Okay, got it.
Those are different emission mechanisms. You have zebra, you have you have fiber burst, whatever. But RFI itself can be different flavors. So, and this is, in fact, depends on the duty cycle of your thing. In fact, it's how you manipulate your data, and what is important. All these results are should be judged in terms of duty cycle relative to your integration time. And you can play with this duty cycle. It's not a real duty cycle. It's relative to what you choose to be your integration time. So you can do that. And RFI can be continuous, can be intermittent, and there are other things of RFI that might not be able to be detected by this. For example, there is a particular, if you read our papers, we show an example of a specific RFI that could not be detected because it mimics Gaussian statistic. It's not Gaussian, but it's so packed, like the symbols of some digital signal link, whatever, that is so densely packed that it may be very close to Gaussian. So you may not have enough sensitivity to